Welcome back. We are in our final installment of Chapter 11. Well, there might be a couple of videos on this topic. But this last chapter is on phase changes. And so now if you're wondering, so what is a phase change? Yes, you already know. You know what a phase change is. A phase change is just referring to something moving from a solid to a liquid to a gas, perhaps even a gas liquid to a solid. So a phase change is just talking about transition between states of matter, solids, liquids, and gases. And that's all this is really referring to. Now the thing is, most people don't put a whole lot of thought into what goes on into a solid, liquid, into a gas, or something of this nature. Most people don't really, again, I don't know how to describe it. They just don't think about it that much. But we have to, in order to do these problems. Say I gave you an ice cube, and this ice cube was 30 degrees Celsius. Say the temperature of that cube of ice was negative 30 degrees Celsius. So you've got a cube of ice, and I said, okay, I need you to melt this piece of ice. So if I ask you to melt this piece of ice, there's a thing. Before this ice will melt, what's got to happen to the temperature of this piece of ice? Well, what's the melting point? Well, the freezing point, you know what the freezing point of water is 0, which means the melting point of ice is 0. So before you can even try to melt a piece of ice, you've got to change its temperature to 0. So before you can melt a piece of ice, the first thing you have to do, and I'm going to write delta T, before you can melt it, you've got to get its temperature warmed up to 0. Now, once you've got the ice to 0, well, congratulations, you can begin to make liquid water at that point. Okay, so let's say you do this, and now here's your liquid water. You've turned this block of ice into a liquid. Well, what's going to be the temperature of that water? Well, the temperature of the water is still going to be 0, because that's where you're at. Now, what if I told you, okay, I want you to turn this water into steam. Well, before you can get this water into steam, you've got to make this water get to boiling. So, before you can get steam, what's got to happen to the temperature of that water? Well, before you can make steam, that water, look, notice what I'm doing, another delta T. You've got to change the temperature of the water again. So if you start with an ice cube at negative 30, you've got to heat it up to 0. Once you're to 0, you may begin to melt. And then once you've melted it, now look at what you're doing. It's like starting over again. You're at 0, so what have you got to do? You got to start heating up the water till it gets to 100. Once you get the water heated to 100 degrees, you can then start to evaporate the water. The water can then start to turn. Let's not use evaporate. Let's say vaporize. That'd be a much better word to use for this. Wow, except for the fact I can't spell vaporize. Anyway, let's say you begin to vaporize the water. And now you're actually turning the water. Draw me a little cloud of steam. So you vaporize the water and turn it into steam. Most people don't think about all these different steps that went into taking an ice cube and turning it into steam. Well, let's first do this. Let's kind of get into this a little bit. Something most people don't even notice. Have you ever put water on the stove? Put water on the stove. Bring it to a boil. To boil water, we just said it. The water's got to be 100 degrees Celsius. You start boiling the water. Here it is. Here's the water. It's vaporizing. Here's the water. Vaporizing. You ever notice something? What happens to the temperature of the water? It stays 100 degrees. You cannot... Why does the water stay 100 degrees? You've still got the water on top of something hot. So why does the water stay 100 degrees? Because once the water hits 100 degrees, you begin to create this vapor. And when you create that vapor, every bit of the energy that you put into that water, all that energy goes into this. This, we call it a name. We call it a phase change is what we refer to this. Now, we've got two new definitions for you to learn. Latent heat of fusion, latent heat of vaporization. Okay, now you're throwing new vocabulary words on us. Well, just like every material has its own specific heat, every material, water included, has its own LF and its own LV. Now, if you look in your textbook, you will have a gigantic chart of these LFs and LVs. Look at all these things. Every material, you can vaporize a piece of lead if you want to. Every material has its own LF and its own LV is all that comes down to. Water, let's take a look at water. So, for water, what is LF for water? LF for water, and this is the only one I have memorized, calories per gram. It takes 80 calories of energy to, and by the way, fusion is actually fusion is talking about this melting, freezing area. This is where fusion comes in. So the latent heat of fusion for water is the energy it takes, and it kind of goes both ways. This is the energy you would need to take a piece of ice and turn it into liquid water, or vice versa, it's the energy you would have to remove to take liquid water and turn back into a cube of ice. Now, LF for water is 80. LV for water is 540 calories per gram. And the reason why I'm doing these, and I know you've got this whole chart with them on here, these are the only two I expect you to memorize. That's it. So this is all I expect you to memorize, are just these two. LF and LV in calories. And those are the easiest ones to remember, 80 and 540. So if you notice, by the way, it's a whole lot harder to boil water than it is to freeze it or melt it, if you notice this different. It takes a whole lot more energy to try and vaporize or condense water than it ever did to melt water in the first place. That's the foundations for all these problems. The basic equation that we are looking at looks like this. Q equals, because we're still talking about heat, but if you want to melt or boil something, the equation is just ml. And then this L can either be an LF or you can write an LV. It depends on what it is you're trying to do. If you're trying to turn a piece of ice into water, water to ice, then it's LF. If you're trying to take water, turn to steam, steam turn to water, then you'll use this LV. But anyway, this is all the equation looks like. So the reality of it is, Chapter 11 only has two equations, MC delta T and ML. And that's the only two equations you're learning. These problems, yeah, they become bigger and they're harder, but it's just because they're combining these together. Just like you can have a problem that says MC delta T plus MC delta T plus, well, you can take a problem that says MC delta T plus ML plus MC delta T plus ML. You can just keep adding a bunch of stuff together. And that's what the hard ones look like in this chapter. There's a little chart you'll see in most of your books, and I want to talk about before I leave and maybe do one example in this video. A very common chart teachers will give you, it's going to look like this. And they're going to come back and say, they just want you to notice something. If you started with that proverbial block of ice at negative 30 degrees Celsius, whoop, there it is, before you can melt that block of ice, what were you going to have to do? You're going to have to add heat and get it up to 0. Once that block of ice is to 0, you can actually start to melt it. But notice something. The whole time you're melting the ice, what does your temperature do? It stays at 0. So you're not going to start to change the temperature of the ice until every bit of the ice is melted. Now, once all the ice is melted, look at what you begin to do again. You start to change your temperature. You go from a 0, and you will keep, if you keep heating up that water that was ice, what temperature is it eventually going to get up to? Well, eventually, it's going to get to 100. And what happens to water once you get it? What's going to happen to the water once you get it up to 100? Well, same thing. Now you're going to start vaporizing the water. So you're going to vaporize the water, and you're going to vaporize and vaporize and vaporize. And after you've vaporized all the water, what will you do to the steam? Well, if you keep heating it, you'll keep getting the steam hotter and hotter. You see this kind of picture in every book, and a lot of teachers want you to kind of understand what's going on. You just need to understand these little concepts. To melt something, the temperature's got to be 0, at least in terms of ice or water. And then if you're going to try and vaporize something, the temperature has to be to 100 before you can vaporize it. These are just little nitpicky things that show up in these problems. Let's see if we can't go ahead and do one of the examples out of the textbook. Oh my goodness. Is that the example we want to do? I think I've managed to skip one of my examples. Let's do this one first. I'm doing them out of order, but this is actually the easier question. And I know when you're first looking at it, it doesn't look very easy. And I'll pause and you can look at it. You remember a little while ago in the older videos, I said power is equal to, we can write Q over T, energy over time. Well, I said in that video we could write MC delta T over time. Well, you've learned a new type of Q equation. The Q equation I just taught you is ML. So this problem is giving you a power, and what it's wanting you to do is just say that power is equal to M, latent heat, over time. So instead of an MC delta T question, it's just an ML question. And by the way, just like in those other problems, you can make MC delta T equal to all these different things. You can do the same thing in this one. You can make ML equal to 1/2 MV squared if you wanted to. But anyway, this question just says, it's giving us, in the problem, it's giving us an LV, and it's giving it in joules and kilograms, which is good, because this problem we got to be in joules and kilograms. And then we've actually got 10 watts, and then we've got, all it asks you to do is find time. So this problem gives you 10 watts, and it gives you a mass of 1. It says that L for helium is 2.09 times 10 to the 4. We ain't going to need a calculator for this. Times time. And then we'll do our math. Time equals 2.09 times 10 to the 4 times 1. We end up with 2.09 times 10 to the 4 divided by 10, which just becomes 2.09 times 10 to the 3rd. And this is time, so my answer would be seconds. There. And this would be a very easy example of the problems. Now I'm going to do some harder examples in the next video of what the real meaty problems are in this chapter. But anyway, so long. Auf Wiedersehen.